Chapter 4 discusses the periodic table. In Chapter 4, Section 1, we begin with Johann Dobereiner, who was one of the first people to put together a periodic table. Now, during his time, there were not nearly as many elements as we currently have, but what he discovered was the law of the triads. And a triad is just a group of 3 elements that he placed in those specific groups due to their similar properties, so they behave similarly. And this is kind of the forerunner of where our current groups of the periodic table came from. He also listed them in order from the lowest atomic mass to the highest atomic mass at the bottom, again similar to the way we currently have our periodic table set up. John Newlands was an English chemist who also came up with a version of the periodic table, and this was in 1865. There were 16 known elements at the time, and he also put the elements in order of increasing atomic mass, and what he discovered was the law of the octaves, which was the beginning of periodicity, meaning that properties repeated after a certain number of elements. In his case, he discovered it was after 8 elements. So every 8th element, after putting these elements in order of increasing atomic mass, you started to get repeating properties. So like sodium shared similar properties with lithium, magnesium with beryllium, and so on. And finally, Dmitry Mendeleev was a Russian chemist, and this was about 5 years later after Newlands. He came up with the what's called the modern periodic system. There were 63 known elements at that time, and he's really considered to be the father of the periodic table. He also put the elements in order of increasing atomic mass, similar to his predecessors, and he also grouped elements of similar properties into similar vertical columns. Something that he noticed that was different from a few of the other scientists was that the elements didn't always fit by increasing mass and by the properties that they should have had based on that particular column. For instance, tellurium and indium, if you put them in order of their masses, they fell into the wrong columns, so he felt like you needed to switch those two. He also left some gaps where he thought something else should fit, and he believed that they just hadn't discovered what that element would be. And it turned out that he was correct on most of those, and we just had to wait for some elements to be discovered before we could finish filling in that entire periodic table. About 40 years later, we're getting into around 1915, and the English chemist Henry Moseley was the first person to put the elements in order of increasing atomic number. He called them a fundamental unit. At the time, they still hadn't discovered protons. It wasn't until 1920 when Rutherford announced the existence of protons that they realized that's what Moseley had been calling this fundamental unit. And his research was with X-ray spectra, similar to the line emission spectras that we looked at earlier. But by putting these elements in order of increasing atomic number, they figured out that that helped to solve some of those discrepancies on Mendeleev's table, where the mass didn't always go in the correct order in order to stay in the correct vertical column and match up with the properties. But if you put them in order of increasing atomic number, then they did line up to share similar properties with their vertical column. The periodic law is just when properties of elements are periodic functions of their atomic numbers. Again, that's called periodicity. So it's essentially just this regular repeating pattern that we're going to see of the properties throughout the periodic table. On the periodic table, there are periods and groups. The periods are the horizontal rows. Along those rows, you're going to have similar electron configurations. They're all part of the same principal quantum number. And then the groups or families are the vertical columns. and within those vertical columns there are elements that are put there based on their similar properties. The periodic table is also divided up into metals, nonmetals, and metalloids. Metals are going to be good conductors of both heat and electricity. We also have a subcategory here called transition metals, which are our D block and F block. And they're not going to be as reactive as our metals in group 1 and 2, but they are still very useful to us. A lot of the elements in that group are used in construction materials, copper wiring, and jewelry. Okay, gold and silver fall into that category as well. Nonmetals are going to essentially have the opposite properties of metals. They're poor conductors of both heat and electricity, and they make up part of the P block, mainly the right part. The semiconductors, or metalloids, are the last group, and they are kind of an intermediate between the metals and nonmetals. They can conduct, but they're not as great as a full metal would be, and they're located along the stair-step line on our periodic table. So that dark line that runs through that P block is what the stair-step is, and that's where the metalloids are located. So things like boron, silicon, germanium, a lot of elements that are used in different sort of electronic devices. The main group elements, which are also called the representative elements, are our S block and our P block. And they're called the main group because they follow a normal, regular electron configuration pattern. The D block and the F block have some goofy rules that go with them, so they are not considered main group elements. There are 8 main groups, vertical groups that is, going across the periodic table. Group 1 are the alkali metals, and they are very reactive. They only have one valence electron in their highest energy level, which means that in order to achieve a stable octet, which is what all elements want to achieve, they will try to give away that electron. Again, they are very reactive. A lot of them will burn when exposed to the air, so many of them will be stored in oils. And they're extremely soft. You can cut through many of them with like a butter knife. Plasmas are thrown in here because when they're at very high temperatures, they are able to help to conduct electricity pretty well. They are the alkali metals. When they're at really high temperatures, they can become these plasmas. So normally we just think of as solids, liquids, and gases as the states. Plasmas, again, are sometimes considered the fourth state of matter. They're just a mixture of cations, electrons, and some neutral particles, and they help to conduct. They're used sometimes in streetlights or headlights, and they can penetrate the like fog a lot better than white lights. Group 2 is the alkaline earth metals. They're very reactive as well, but they're a little bit less so than Group 1. They have 2 valence electrons, and therefore they will be trying to get rid of those 2 in order to achieve their octet. And they're going to be a little bit harder and a little bit stronger than Group 1 elements. The lanthanides are actually located at the bottom of the periodic table. They're our 4F group, and they are shiny transition metals, and they are in different things like lasers, sunglasses, TVs. So there are some different properties that they have, but they are shiny and metallic, just like the rest of the metals. The actinides are directly below the lanthanides on the periodic table. They're the 5F group. They too then are shiny transition metals, and many of them are going to be radioactive, which we discussed before meant that they have an unstable nucleus. Probably one of the most well-known actinides is uranium. Now skipping across over to the P block, the 13th group across is the boron family. And boron consists of metalloids and metals because it breaks through that stair step through the p block. One of the most common elements in this group is aluminum. Believe it or not, aluminum actually used to be very rare and expensive. This group has a charge of 3+. Okay, they have 3 valence electrons that they will try to get rid of in order to achieve an octet. Group 14 is the carbon family, and many of the elements that are important to life, obviously carbon, and then silicon and germanium, as I mentioned before, are present in a lot of electronic devices. And at this group, we have reached the point where elements have 4 valence electrons. So they could either gain 4 electrons to achieve an octet, which would give them a -4 charge, or they could give away 4 electrons and have a 4+ charge. So we say they are 4+ or minus. The nitrogen family is group 15, and obviously you know that nitrogen makes up the majority of the atmosphere, and nitrogen and phosphorus are also key ingredients to living organisms. This group has 5 valence electrons. They're the 5th main group, so they have 5 valence electrons. So they are going to try to gain 3 more electrons in order to achieve an octet. So they would have a 3- charge. Group 16 is the oxygen family. Oxygen, we know, is necessary for us to breathe. Some other elements that are in that group, sulfur's one of the next ones. Sulfur has this yellow color to it. It's kind of a rotten egg type smell that you're going to get from that. It's one of the smelliest of the elements. And the oxygen family has 6 valence electrons, so they would have a -2 charge to achieve an octet. The halogens are an important family. In Greek, they literally mean salt former. They're the most reactive of the nonmetals. They have 7 valence electrons in their outer energy level, so they only need to gain 1 more, which is what makes them so reactive. A lot of times they will combine with metals to form salts. So anytime you have a metal and a nonmetal that are combining, that is called a salt. So it's not just NaCl, it's any metal with a nonmetal. For instance, this one here, we've got potassium, which is in group 1, combining with chlorine, which is one of the halogens. And this potassium will give its electron to the chlorine so that it has an octet and will form the salt potassium chloride. And then group 18, or the last group, is the noble gases. And the noble gases used to be called the inert gases because they were originally thought to be completely unreactive. Now we know they do have a very low reactivity, so we no longer call them inert. They do have 8 electrons already in their outermost energy levels, so they are stable and don't really like to combine with other things. However, some compounds have been made with them in a laboratory setting, such as combining xenon with fluorine. That was done in 1962. Some common ones in this group, helium and neon. Just kind of an interesting fact about neon is neon's color is actually only a reddish orange color. So in order to get these other colors, such as the greens and yellows, you have to actually mix them with other gases. And the last group is hydrogen. Now, hydrogen is a group all on its own, and it's one of the most common elements. It reacts with lots of different things. It mostly forms a 1+ ion, just like the alkali metals that it appears above, but it can be a 1-. At that point, it's called a hydride. And with hydrogen, one of the things that has been looked into in the past years are using hydrogen as an alternative fuel source.